right now, exactly right now, we have a dry condition. We have a drought actually problem in most region of the Iran, and also it's referred to the lack of the precipitation in the spring and in the winter. And right now we are dealing with this problem in the most part of the Iran. Here you can see the weekly average time series of VCI and TCI, and also VHI. Again, in this time series analysis, you can see that in 2008 is a based on all of these indices. The 2008 actually is defined as the wet, as a dry year, and also here you can see in 2019, because of the huge amount of precipitation in the winter and in spring, actually the condition of the vegetation and the temperature is quite good. In the second part of this study, we compared the correlation between the different time scale of SPI. You can see the 3-month SPI, 6-month, 9-month SPI with different time scale of agricultural drought indices. As you can see here, there is a correlation. There is a coefficient of determination maps between the remote sensing based drought indices and in-situ station based drought indices. Here also you can see the maps between the SPI and VHI and also TVDI. As a result of these maps, you can see here, this is the correlation coefficient of 6 months VHI with 6 month SPI. For this VHI for 6 months VHI, we found the best correlation coefficient with the SPI, which in most part of the Iran, especially in the western part and also in some northeastern part of the country, which is mostly covered by the agricultural crops or shrub crops or grasslands. There is a very good correlation between the meteorological index or SPI index and VHI, and I can say we can use the VHI for agricultural drought monitoring. Here you can see also the results, the coefficient of determination between the SPI and other indices in different lands cover. As you can see in all of the lands covers, the VHI perform best, and after that the VCI perform well. And also we found that there is a good correlation between the 6 months VHI and 6 month SPI, but with 3 months lag times. As a concluded of this study, I can say that the correlation between in-situ and TRMM precipitation data is high at the monthly and annual scale, and it is followed by SPI. Then we can use TRMM data or maybe other satellite-based data for the precipitation for droughts monitoring. Regarding the relationship between the meteorological and agricultural droughts, the highest correlation was found between the 6 months meteorological droughts or SPI from the January till June and the 6 month agricultural droughts or VHI from the April to September. Therefore, there is a 3 months lag time between the SPI and agricultural drought index. Among the remote sensing based indices, the VHI perform best, and also in terms of spatial distribution of drought, there is a significant difference between the indicators. Therefore, it is necessary to select the appropriate drought index for each specific region of Iran, depending on the land cover, climate, and other criteria. Also, I suggest to use and evaluate the other drought indices related to the evapotranspiration. I believe that the evapotranspiration maybe is the best indicator for drought monitoring. Also, at the moment I'm doing research on that. Also, the soil moisture, groundwater, crop biomass, snow cover, and other indicators. We should evaluate the performance of combined remote sensing data, which we are doing right now. And it is really recommended to develop a remote sensing-based web-based system for online drought monitoring in Iran. Here you can see some operational web-based system for drought monitoring in the world. There are at the moment which I'm talking. There are lots of, not lots of. There are some web-based system for drought monitoring, which researchers can use them for calculating the droughts or maybe for monitoring that. Here you can see some list of that. Also, you can see the list. You can see the list of these websites in the portal of the UNOSA. Also, I would like to show you very shortly a video which shows the web-based system which we developed. I with some of my students developed for droughts monitoring in Iran. Here you can see, unfortunately, this is just in the Persian language. We developed a web-based system for droughts monitoring in Iran. It includes different kind of satellite data, precipitation, temperature, soil moisture, vegetation cover, and with different time scale. And from the different source of data, we can choose the data, and after that we can choose the time scale for the monitoring between from the 2000 till now. And after that, in the first step, we can show the results on the web system after choosing the dates. Then you can present the results here. This is the classified map of the precipitation. For example, this is the monthly precipitation. And also with clicking in each pixel, you can get the time series data of each pixel of the precipitation and also of other data. And also, if you have a shape file, you can extract the area of your interest. Sorry, let me go a bit fast. If you click on each pixel, you can get the result, and also you can download this data as an Excel file or maybe as a JPEG file or different formats. I'm going, sorry, a bit fast, and you can download it. Here also the TRMM data. This is the land surface temperature data and time series of that. This is the NDVI and time series of NDVI. And also based on these data, we can calculate just online different kind of drought indices, including the SPI, VCI, TCI, VHI, and others. Here, for example, you can see the SPI data with different time scale. With different time scale, 1 month, 2 months, 3 months, 6 months. You can choose the time scale, and also you can choose the period of, and then you can see the maps of the droughts for the area which you choose, and also with the classification. You can download this data, or maybe you can get the result for each pixel, the time series analysis of each pixel, or even you can download or you can extract each part of that by the shapefile of your region of interest. Here you can see the time series of the SPI and also other indices, VHI, TCI, and SPI. Unfortunately, we didn't have good amounts of resource and fund to extend these websites for the entire of Iran. If we find any source of funding or financial support, we can extend this web monitoring system for the entire of Iran or Middle East, or even for entire of the world. And also we are trying to work on some early warning droughts monitoring system in this area as well. Okay, that's so on. Thank you very much for your attention, and please let me know if you have any remark or question. Thank you very much. Professor Mubashiri, can you hear me?
آقای نجار منو بس کنی لطفاً.
موضوعشو اینو بگو.
I thank you very much, Dr. Saeed Hamze, Associate Professor of Remote Sensing and GIS, Faculty of Geography, University of Tehran. I think we missed Professor Mubashiri because of technical issues. Now I'd like to introduce Ms. Veena Shashikant, University Putra, Malaysia. I asked kindly to deliver her presentation with titled Application of Satellite Remote Sensing to Regional Agriculture and Water Resource Management. Madam, please go ahead.
Do you hear me?
Madam, do you hear me? Oops. Dr. Shirish, do you hear me?
Yes, please.
Can you hear me now?
Yeah.
Yeah. Yes, please.
Yes.
Yes, Fatima.
Should I share my slides or would? Yeah.
Your presentation is loading, but it's okay if you prefer to share yourself.
I can share myself. Yeah.
I think it is shared already. No?
Yes.
Before you start, Madam, let me ask all the respectful speakers to finish each presentation in 15 minutes, please, before the shortage of time. Thank you very much.
Okay. Good evening, good afternoon, and also good morning to some of you in different parts of the world. A very warm virtual greetings from Malaysia. Thank you, Professor Muhammad Mubashiri from Iran, the moderator, and also special thanks to the United Nations Office for the Outer Space Affairs and Ministry of ICT from the Iranian Space Agency for the opportunity for me to share my research work. And my research work is entitled Utilization of TVDI and NDWI to classify severity of agricultural drought in Chuping, Malaysia. This research work consists of not me alone, but there's a team behind this. Myself as a PhD candidate in Department of Biological and Agricultural Engineering from the Faculty of Engineering, University Putra, Malaysia. So my supervisory chairman, Professor Surveyor, Geospatialist Dr. Abdul Rashid Muhammad Sharif, a professor in the same department, as well as a senior lecturer, Dr. Emrun Wayayok, associate professor in the same department, Associate Professor Dr. Muhammad Raushan Kamal. I have Dr. Lee Yang Peng from the industry in the company of FGV R&D, and also Professor Dr. Wataru Takeuchi from the University of Tokyo, Japan, to support this research work. Agricultural drought here we refer as a declining of soil moisture content, where we can affect the crop for stress and also productivity.
نه درست شدم. نه یاد با موبایلم وصل شدم. درست شد. آره خداحافظ.
So here we can say that the crop stress can be sort of like separated into two sections, but I will discuss some of the challenges just later in the slides. Here the impact, I would say that whenever we say agricultural drought, somehow the irrigated areas will have lesser impact or less severe due to reservoirs, and also maybe even there is no rain, but the reservoirs and the water supply is still there to support the crop. But in the non-irrigated areas, we always see that the crop will only depend on precipitation or the rainfall. So that's where actually non-irrigated crops are considered to be more affected. And in these circumstances, what will be the limitation for the crop productivity will be the frequency of the drought condition and how the global climate change also is happening around that region. Here, if you can see on the left-hand side, there is meteorological drought that will happen first. And when there is time goes on, when there is less rainfall and seasons gets hotter, agricultural drought will come in where there is a soil moisture deficiency, and plants will be actually stressed, and this will definitely affect the yield. So that's where I would want to catch my thoughts today. For my objective here is that if we use the spatial indices like the normalized difference water index and also temperature vegetation index, this understanding of the agricultural drought can be explored. So for normalized difference water index, we sort of see the amount of water on the vegetation canopy. Yes, there is some errors in this index, but somehow we can say that the performance of this index is good enough even when there is a saturation at a higher level. That's according to the reference, and it's also sort of used most frequently to assess drought, and where we can see that emphasis is on the moisture content, on the vegetation. When we looked at the temperature vegetation difference index, the concept is a little bit advanced, where we can say that the Sandolph 2002 study has came up with a very good indices, temperature vegetation index, for getting to know sort of the root zone moisture content. And this is actually looking at the NDVI values in respect to the land surface temperature, where we can see that the bare soils and the partially covered and the fully covered soils will be having this proportion embedded into the indices. Yes, of course, there is also many other indices that we can look at, like just discussed previously from the last presenter. We have vegetation condition index, we have temperature condition index, we have vegetation health index, we have SVI, standardized vegetation index, and we also have normalized difference water index and temperature difference index. So I only would, with the time limitation, I did this research on these two parameters. You can see NDVI and TVDI. And the objectives of this indices used was to determine the agricultural drought, to see how these both indices was going into this study area, and also if we can separate this agricultural drought prone area to severity, or segment them into class. So the data used for this research was simulation meteorological data, also getting the satellite data, satellite meteorological data from Jasmine GCOM from JAXA, and also I used Landsat 8 images for 2015, 16, and 17. And there were other years that I would wanted to use these Landsat images, but due to the cloud covers issue, I couldn't use the other years. And as you can see, there's a map on the bottom right, and that is actually the Peninsular Malaysia. And if you can see the gray map, that is actually the state which is adjacent to Thailand, I would say southern of Thailand. And the colorful big map, you can see that is actually the district of Chuping Perlis, which is said to be one of the hottest area in Malaysia and so-called hotspot of the country as well. The meteorological data, if you were wondering why would I use just the specific months, is because also due to cloud cover, as you can see. In the other months, apart from February and March, April to December, if you see the graphs, you can see that the average precipitation is quite high. So the non-irrigated crops are okay. But when you see in February and March, there is very little rain observed. And if we use the Malaysian Meteorological Department data, we can see that the dry spell in the years 2016 had 43 days in day by day there was no rain, and about 2015 for 20 days and 2017 for 22 days. So what I did with the Landsat image was that I got the difference water normalized difference water index, and I also took the NDVI index and the temperature vegetation index. The steps to derive the land surface temperature was using the Landsat 8 band 10. I converted it to get the spectral radiance, getting the atmospheric brightness temperature, and getting the land surface temperature, but embedding into that proportion of vegetation, have used the NDVI and also the land surface emissivity. So from that results, I have taken the Moran's eyes approach, because this we can access this partial correlation in geographically that area of study area. So here I used a Z-score to allow me to differentiate the severity of the agricultural drought. As you can see, the formula is on the slide there. And the results from this was that, true enough, we had some parts of the region in the district, Chuping district, to have higher water deficits. And you can see the brick red colors in the map. That's where the lowest water content was in the vegetation and also in the soil. So here we can say that the NDVI for the area overall was about -3, 0.3, 0.37, and 0.36 for the 3 years that we are looking at. And once we see the temperature vegetation dryness index, as you can see the map, the red colors here shows that the areas are mostly affected and said to be more dry compared to the blue ones, which is generally more wet. Here we can say that in 2015, about...
Excuse me, Vienna, I'm interrupting you. We
Yes.
are almost 20 minutes behind the schedule. If
Okay.
you please just make it in few minutes time. Thank you.
Okay.
Thank you.
So moving on. So here, this is the part where I actually use the Z-score to show that the red area in this drought hotspot, the red area is the most severely affected. And if we would want to do any mitigation or any approach to look into this drought, or let's say crowd seeding or anything, then probably this information would be where we want to start off the red parts. And yeah, so I would say that it is a it is an attempt to actually understand and use the temperature vegetation index to segregate the significant areas of this hotspot using the Moran's eye spatial relationship. That's all. A complete reference can be found in the slides here.
Thank you very much for your interesting presentation. Thank you. Our next speaker would be Professor Nishikari, Professor Masahiro Tasumi from Japan. Would you please take that 15 minutes, no more than 15 minutes time for your presentation. We are
Yeah.
a lot behind the schedule, please.
Okay.
Thank you.
Can you hear me?
Yes, I can hear you.
Okay. So let me start my presentation. Maybe I can put my camera on. Okay. Hello, and thank you very much for having me a chance to join with this interesting workshop. My talk is about agricultural water management using satellite images. And actually, one of the examples I'm going to talk is about northern part of Iran, working with Iranian people, Urmia Lake Restoration Program, and Sharif University of Technology, and Japan International Cooperation Agency. Please go next. Next, please. Okay. Okay. This slide just want to show you the water, freshwater resource will be a big issue in near future, and more and more people have a problem about water resources. And also the agriculture is the primary user of freshwater. 70% of freshwater is used for agriculture. On the right-hand side, this figure shows the relationship between evapotranspiration and crop yield. Evapotranspiration is an important key part for determining agricultural water demand, because, as clearly seen in this picture, the more evapotranspiration derives more crop yield. In this case, it's a wheat yield. But if evapotranspiration is short, it means that the crop gets water stress and it derives less yield. Next, please. Next, please. Yes. And this is why lots of people in the world, lots of researchers in the world are now working for evapotranspiration estimation using satellite images, because satellite image is very powerful tool to describe evapotranspiration spatially and temporally. And actually now FAO, Food and Agriculture Organization, is having a webinar series of remote sensing determination of evapotranspiration. So if you are interested in this kind of topics, please search for this so you can access to a very good amount of information. Next, please. Okay, and there are some popular methods available, but probably the most popular methods, especially for agriculture application, using satellite information to evapotranspiration estimation, is Siebel model and metric model. These are very similar models, and I just want to briefly explain how they estimate evapotranspiration ET. Okay, satellite information, as you know, the vegetation, seeing the vegetation is very good at using by satellite, like NDVI and leaf area index. But also from satellite, you can make energy balance, radiation balance, like surface temperature, it's thermal radiation, and also shortwave radiation, like visible area, near infrared area. There are lots of information available from satellite. So we can calculate how much energy, radiation energy available at surface, and also how much portion of energy is used to evaporate water. That's how these models estimate evapotranspiration using satellite images. As the previous presentation says that temperature, surface temperature is very strongly correlated to the soil moisture and wetness. So thermal information is also very important, because cold surface means wet surface. Hot surface means dry surface. So how much portion of energy used to evapotranspiration is also reflected as temperature. Next, please. Okay, this is an example of how evapotranspiration information is used in agriculture water management. This is for Asian Development Bank project, and it was for Tajikistan irrigation district. The left map is NDVI, vegetation. And the red colored area means that vegetation is weak. So agriculture is not very successful. The right side map, it's about water derived from evapotranspiration. And the red colored area means water shortage, not sufficient amount of water available at field. So because of the field water is not sufficiently available, the weak vegetation means weak crop production. And this type of information is very valuable for agricultural water management, especially evapotranspiration is a quantitative information. So we can tell them how much cubic meter of water is not available in this area in this timing. So this helps them to planning for future, like how what kind of infrastructure they need and how much investment they need. Next, please. Thank you. This is about the impact of climate change for agricultural water demand, field water demand. And this was for a World Bank project and for northern part of Afghanistan. Actually, the primary part of this study, thinking about future water demand, is based on global climate model, GCMs. However, in this case, in northern part of Afghanistan, we don't have sufficient information at ground for current status of agriculture. So of course, satellite is very powerful tool to monitor the current condition of agriculture and practices. So based on the satellite monitoring observations, we can make a very good start line to think about future. Next, please. Okay, this is about Iran. Northwestern part of Iran, we had a project about water balance and hydrological modeling. Okay, as I think most of you knows that the Urmia Lake, which is a very famous lake in northwestern part of Iran, but that area had a problem. The water is not balancing and not a sustainable way of water management was conducting. And Urmia Lake Basin was a closed basin. So primary input is precipitation, primary output is evapotranspiration. However, because of less precipitation and more evapotranspiration because agricultural activities, the lake became smaller and smaller. Fortunately, I think these 2-3 years, they have good amount of rainfall, so the lake is recovering a little bit. However, thinking about sustainability in water management, water balance is very important for the region. Next, please. And our project itself was about making hydrological modeling. And I am a specialist of evapotranspiration, so we study about evapotranspiration from satellite image, which will be a very good input for hydrological modeling. Next, please. So this is the pictures, snapshots of field surveys. I really like that area very much. And knowing the agriculture activity and irrigation style and field management is very important, I think, for making this type of study. So we made some field surveys. Next, please. And then especially Remote Sensing Research Center of Sharif University of Technology made the evapotranspiration map using MODIS based in scale. That's a very good data set. However, it's a very typical question in this type of study, but how much accurate or how much reliable that estimated evapotranspiration map is a big question. However, unfortunately, with MODIS resolution, spatial resolution, it's very difficult to evaluate the accuracy because the field size, agriculture field size is very small and complicated. That's why we compared Landsat-based evapotranspiration to actual field level, and also Landsat evapotranspiration to the MODIS evapotranspiration. By the way, this is MODIS evapotranspiration is made by metric evapotranspiration estimation model. Next, please. Okay, this is a comparison, accuracy assessment. X-axis is the ground-based estimation for some specific agriculture field, and Y-axis is for from the satellite estimated evapotranspiration. Fortunately, in these areas, our estimation was probably successful. This is about the satellite image date and type. Next, please.
Excuse me,
Yes.
Professor Tasumi, you
Yes.
got 2 minutes left, please.
Okay,
Thank
yeah. This is about monthly comparison, and for apples, grapes, their soils, our estimation is probably good. Next, please. And this is about annual comparison. For apples, their soil, grapes, the black ones are ground-based reference values, and gray ones are from satellite images for some sample fields. And the agreement was very good. And of course, the satellite information, it includes many different types of land uses. So for rain-fed wheat, irrigation, crop, city, and so on, we can estimate evapotranspiration. This was difficult to estimate from ground-based measurement or estimation, but from satellite, we can provide those kind of information. And here, I think one important thing is communication with non-satellite communities is also important. Sometimes we need communicate a lot. And for example, in this case, because from the field surveys, a typical amount of irrigation for apple cultivation is about 1,800 millimeter irrigation. Okay, and apple field has rainfall also, so more than 2,000 millimeter per year has inputted or supplied to apple field. And according to our result, evapotranspiration, estimated evapotranspiration for those kind of apple field is about 1,200 to 1,300 millimeter, which means about 60% of irrigation plus precipitation is used as evapotranspiration. 40% goes to the drainage or to groundwater recharge, seepage, or percolation. And this is quite, I think, the reasonable values for their irrigation style. So with this kind of information, I think it connects between the satellite information and traditional types of agriculture engineers. Okay, so I think this type of additional information is important. Next, please. And next, please. I want to skip this. Okay, this is the last one. This is just for kind of advertisement of a new Japanese satellite, GCOM-C. GCOM-C has been launched on December 2017. So from 2018, we have data and 250 meter resolution visible near near-infrared and thermal, 250 meters thermal available for once every 2 days or more. And I think it can help a lot for, especially for agriculture application. So this type of information, for example, evapotranspiration maps in the world, helps scientific-based water management in future. So I think it contributes to sustainable development using space. Okay, that's all of my presentation. Thank you very much.
Thank you, Dr. Tasumi. Audience asked for your email address. You can go to the comment and leave your email, please, if you wish. The next speaker, of course, the next session was, the next 15 minutes was left for discussion, but because we are behind the schedule, we prefer to leave this discussion at the end of session and give more time at that time. Right now, I'll ask our next presenter, Professor Oja, to present his talk about space technologies for early warning, preparedness, and response. Are you there, please? Are you here? Okay, please. I invite you to start. Yes, go ahead.
Thank you. And I will not take much of your time. I will try to wind up in just 15 minutes. Good evening, ladies and gentlemen. We are here to present some emerging concept with respect to the space technology for early warning, preparedness, and response. And next slide, please. Something about me. So I'm basically a postdoc in AI and with specialization in the aerospace security, and representing an organization, BASIL. It's a Broadcasting Engineering Consultant India Limited, basically working in the satellites and solutions. Next slide. As you know, that's early warning. The term early warning is used in many fields to describe the provision. So on emerging dangerous circumstances where that information can enable action in advance to reduce the risk involved. And same as basically the ecological monitoring is also the system of regular long observation in space and time. So we'll not go into theory. Next slide, please. Elements of early warning, we know that's basically the early warning. We had categorized the things into 4 parts: the risk knowledge, the monitoring and the predicting, disseminating the information, and response. And we just want to tell you that as of in an Indian context, we are using these 4 contents in basically the amalgamation of artificial intelligence and the machine learning in basically climatic change. So a growing realization that climate change impacts are not isolated, threat instead, needing more holistic response alongside addressing the social issues. So it's a kind of 4 elements we have amalgamated, and we have come out many solutions which basically talks about these things. Next slide. As of now, the space technology for early warning in a global aspects, we know that the UAV aerial photographs extents an impact of environmental disasters like landslides and erosion hazards. Then Earth observing satellites images, assessment and monitoring process of deforestations and drought floods, meteorological satellites, weather forecasting, assessment prediction and monitoring of drought, flood and large-scale fire hazards, then satellite radars, and then satellite laser ranging, basically monitoring and recording earthquake and volcanic activities. These all things, technologies we are being using in the Indian context, and Indian space system have used these technologies to predict drought and increase bushfire risks up to 5 months in advance and more than that. So we should use the data from the multiple satellites to measure the water below the Earth's surface with unprecedented precision, and were able to release these to the drought impact on the vegetation several months later. The way these satellites measure the presence of the water and there is something amazing. It's mind-blowing. And we have been realizing we have been taking the good impact and good result from these particular technologies in the Indian space system. Next slide. So in the global aspect, we know the Economic and Social Commission for Asia and the Pacific efforts related to space application Gateway for Disaster Reduction, Regional Cooperation, RSAP is there, DRR and CCCA are integrated with development, which basically enhance disaster preparedness, early warning at a community level, and this currently it goes on increasing. Next slides. Regional international initiative, we are talking in context to the Indian regional cooperation initiatives, Continental Asia, Asia Pacific Regional Space Agency Forum, then we have Satellite Constellation for Disaster Monitoring, then the international initiative, basically the UN Platform Space-Based Information for Disaster Management, UN SPIDER, ESCAP, UN SPIDER, International Charter on Space and Major Disaster. This is something we are talking about the global at the macro level where the international organizations are collaborating with the Indian system, space system. Next slide. So let's talk about the Indian supportive role under the framework for the Asia Pacific Regional Space Agency Forum, APSWAP initiative in Central Asia. ISRO support the disaster management activities in Asia Pacific region. ISRO is the signatory of International Charter, Space and Major Disasters, support authorized users of the charter during, and ISRO also support the disaster management activities of UNISCAP under regional corporations. Next slide, please. So Indian Platform Initiative, when we are talking about that, ISRO disseminates relevant information from various sources, space technology, ground sensors technology, crowdsource, etc., to interactive geospatial domain through various geoportal under disaster management support system, DMS program we call it. And we have a couple of programs that Bhuvan, the National Database for Emergency Management, where we have got the pool of the data. We collect from these various sources and we do kind of a predictive analysis. We have got solutions where we are able to predict more than 5 to 6 months advance things. And then meteorological and oceanographic satellite data archival centers we have got. It's a kind of a database for the administrators to better understand the impact and for the improved decision support and effective, you can say, decision-making system. Next, please. So when we are talking about the India's early warning preparedness and response for flood from cyclones, preparedness with large coastline, India is susceptible for cyclones, so understanding the impact of cyclone with respect to its earlier footprint, low-lying areas can be achieved through the satellite imaging. We have got polar satellites also, we have got other satellites which are capable of getting the footprints and doing a kind of a real-time predictive analysis and giving to us. And using historical data, we have got the archive of those things. And those systems are well advanced with the ML, machine learning, kept on getting the new data, teach them, and then they create a kind of effective predictive system. So it's an early warning system we have got in ISRO, where basically ISRO uses geostationary and low Earth orbit satellite for providing experimental inputs on the cyclogenics, cyclone tracks, cyclone intensity, and inset series of satellite which the government of India or the ISRO, the Antariksh, who takes care of this. With frequent image provide the cyclone parameters for the real-time analysis. We are much more capable of doing that, and we are improving day by day. And response near real-time information on induction due to the cyclones derived using optical and microwave SR data is also provided to the concerned department for public announcement in a real-time basis. I mean, there will be a kind of a latency, say, for around 4 to 5 minutes or something like that. But it's something we are trying to cope it and make it more real-time. So in fractions of a second, it will be intimated to them. Next slides. So we have got a case study. You can say there was a cyclone Yas, location Odisha, India. Satellite data, Sentinel IONSAR, this is the period. And then the Redisar 2SR and cyclone, heavy rain effective in parts of region. We were incapable of identifying these particular cyclone, and we made alert of we make necessary arrangement for the disaster management, and then the things were not it was amicably controlled, and we can take a preventive measures in a much more advanced. Case study 2, next slide, please. Case study 2, we have got the cyclone Tautakete. It's basically in the Gujarat province of India. Satellites data we were used and see the heavy rain in parts of Junagadh district of Gujarat state, and where we were able to get the real-time pictures and imaging, and thus we were able to do a kind of a remedial measure much before the things happened. Next slide, please. So when we are talking about the Indian Emergency Warning Preparedness and Response of Flood, we are prepared on the education of static data during major floods in different states. Floods, hazard map layers were prepared for entry country, early warning system. We have got historical modeling of satellite, ground-based hydrometeorological inputs and digital elevations model. Spatial flood early monsters was selected through like Brahmaputra. We have got a river by the name of Brahmaputra, which flows along the Assam. Then the response, near real-time information on the flood inundation derived from optical and microwave. Thus, you can see that we are using all modes of communication, all kinds of technology to overcome and create a kind of early preparedness for these kind of systems. For climatic and weather application, a symplectic characteristic is a big data as a collection for analysis of meteorological on the Earth system related measurement and high spatial and temperature resistant systems output. Then ML is also used as a refining and discovering new linkage between location, times, and the data set, and where features prediction over AI is also building on connection that ML discovers to provide automated warnings and advice to society of approaching weather extremes. Next slide, please. Next slide. So case study 3, you can say flood early warning. We have got a warning system, flows in Assam, where we have got sensitivity data. Then we have got MOSDAC, WRF, and thus ground hydro monitoring, computed high discharge, synoptic weather predictions, catchment, and these things which we have discussed earlier. Next slide. So a kind of a roadmap, basically we can categorize into 4 funnels. So existing policy, we are working on that. Then preparedness and response, collaboration, network expansions. Then real-time data sources, network expansions, and then the improve awareness on the preparedness and response, and incorporating deep learning AI early warning systems. Next slide, please. Next slide. So this is all from my side, and basically we want to say that types of the platforms, we are using the remote sensing techniques, including the satellites, aircraft, helicopters, and UAV, depending on the extent of area, types of the output, RGB, NIRs to be surveyed and analyzed. Platforms are decided and used. We are working on the sensors. There are different bands which we are incorporated, and the satellite, Sentinel, Landscape, Rapid Eye, and a lot of things. That is from my side, my submission in front of the forum. Thank you very much.
Thank you, Dr. Oja, for your time being on time. Thank you very much.
Thanks.
The next speaker is myself, and I have a problem of connection early at the beginning of the meeting, and I try to make it up to you and compensate for the time delay. I do my best, but if you give the microphone to a university professor, you can barely get it back. So don't count on it anyway. My talk would be about heat island detection on 4 meters spatial resolution, which is a big problem right now for fuel consumption, for all other problems that we are dealing with for greenhouse effect. And these things is very important to look at the cities and try to find those areas which are unusually hot and try to change the albedo and these things to make a little cooler and easier for the people to live. Please, next slide. Then what is the heat island? Everybody knows heat island is the unordinary temperature heat up. Of course, I lost one of these slides. So compared to the rural area around the city, the big city, industrial city show this effect very much pronounced. It depends on the surface albedo and emissivity. the amount of temperature differs from one surface to the other. I want to skip these things to get to the next point because everybody knows about heat island. Please, next slide. Of course, different sensor and different platforms can detect heat island, spaceborne, airborne, weather, balloons, and everything can detect it heat island. Temporal and spatial resolution is very important. How often we can see these phenomena. And every way that we are looking or monitoring the heat island must be cost effective. Daily monitoring is preferred, is completely preferred for further action to be taken. This makes the spaceborne thermal sensor bands suitable. Geostationary thermal bands are quite good, but quite good in temporal, but poor spatial resolution they do have. Modest thermal bands every 1 by 1 kilometer, which is still poor. You cannot, get more information from the city or critical area, critical regions within the city in the 1 square kilometer pixel. Problem of mixed pixel is another problem. So we have different surfaces with different emissivities, different temperature in 1 pixel. And this temperature that we get from modest thermal bands represents nothing, actually. No surface can be, a good representative for this temperature. Next, please. A problem of emissivity, again, is a big problem that we have different surfaces with different emissivities. What is needed is the sensor with high spatial resolution of about around meters. But these kind of sensors do not carry thermal bands, so we cannot use them. Landsat has the thermal bands and fairly good spatial resolution, but each 16 days it can pass 1 point, and we cannot get real-time heat island detected. So GeoEye has very good spatial resolution, about 1.64 meter, but thermal band, it doesn't have any. So a combination of these two, or fusing GeoEye and MODIS, is what we did in this work, and I'm going to explain it. Please, next slide. So the methodology we used, don't miss, okay, thank you. We just georeferenced GeoEye in Tehran metropolitan. Tehran is a big city, let's say 3 kilometers by 24 kilometers or 25 kilometers. It's a very big city. So we resampled GeoEye to 4 meters, and we classified these GeoEye supervisedly for soil, vegetation, roof insulation, asphalt, stone pavement, and which these two are impervious surfaces, and water bodies. Validation, for validation, we use Google Map and the field observation as well. So we classified each pixel, we assign a class to each pixel of 4 meter by 4 meters. Next, please. Next slide. Okay, this is the classified image for these different classes. Next one, please. Okay, we selected cloud-free MODIS, land surface temperature, and emissivity products. Overlaying GeoEye classified image previously I showed on the MODIS surface temperature LST, and calculating the fraction of each surface cover or each surface class in each modest pixel. So let's say 0.2 of these classes were concrete, or 0.5 was vegetation, or something like this. We calculated this. Please, next. Okay, so we wanted to measure the temperature at the satellite passage time. So we used different thermometers, many thermometers, and we cross-calibrated these thermometers to each other to better than 0.01 degrees Celsius, which is not needed. That much precision was not needed. So 2 weeks field campaign were run for in situ measurements, and we found there was no good correlation between temperature of different class during whole day. So next, please. As you can see this in this slide, the temperature change in 1 day, I showed it here. You can see there is no correlation between temperature change in different surfaces with respect to each other. So we cannot calculate the temperature of one pixel from one class compared to the other class. There is no proper relation between these two. But one point is very important here. At the time of satellite passage, the temperature of different classes do have some linear relationship with each other. That means at the very time of satellite passages, we measured the temperature and we draw these scatter plots of one with respect to the other, and we found very nice linear equations. Go to the next, please. Look at this. The vertical is, let's say, the first one is soil, and the horizontal was vegetation. So soil with respect to vegetation, asphalt with respect to vegetation, and stone with respect to vegetation, and impervious surfaces with respect to or insulation surface with respect to vegetation. The next slide, please. Some of them are poor, but this one here, vegetation with respect to stone, vegetation, soil with respect to stone was better correlation. You can see, let's say, insulation with respect to stone has a correlation of 97%, and the other one was 98%. So some of these surfaces can be calculated from each other. They do have a temperature at the time of satellite passage only. Next, please. You can see again, the relationship is good. It's not perfect, but later on you will see there are some errors involved with this kind of measurement. But what we are looking for is something that we need only a comparison between different surfaces around the city. Next, please. Next, please. Okay, next, please. These are those equations. Okay, what we have did, what satellite receives from one pixel is a combination of the emanating radiation from different surface covers based proportional to their fractions. So L of sensor is equal to, let's say, fraction of vegetation times radiation emanating from vegetation, and so on and so forth for the other classes. So when we are dealing with the wavelengths of 11 to 12 microns, which is the proper wavelengths for calculating the temperature, surface temperature, there is a linear equation, a linear relation between radiance and temperature in Kelvin. So L equal alpha times T, where alpha is a constant coefficient. So based on this, the equation above the first one turns to this one, to this equation. So T of sensor, what sensor measures, which is LST, is equal to fraction of vegetation times temperature of vegetation, plus fraction of soil times temperature of soil, fraction of asphalt times temperature of asphalt, and so on and so forth. So this equation is used for this research. Go next one, please. So, yeah, go back one. Okay. So the T of soil based on vegetation. Which why should I take the vegetation as a main surface to calculate the other surface temperature through the vegetation? It depends on the pixel availability or the surface or the surface cover, which takes a bigger part of the pixel. This can be found from those GeoEye pixels, the GeoEye classified image. So if in one pixel, let's say vegetation has 70% occupied in the pixel, so we take the temperature vegetation as the principal surface and calculate the other surface compared to the vegetation. Let's say, for instance, for this one, T soil is equal to this one, T asphalt, T insulation, and T stone is calculated on vegetation. We put this equation on the above mentioned equation. Go to the next, please. We insert this these four equations inside the above mentioned equation with this coefficient. Now we have only one missing parameter, which is T of vegetation. A and B are calculated for each pixel. TS is LST, which comes from satellite. So T veg is missing. Go to the next, please. When we calculated T wedge, then in each pixel, T temperature of different classes can be calculated through these equations. Go to the next, please. This is the first picture of temperature or LST temperature for different surface cover in 4-meter resolution of GeoEye. And as you can see, the detail is so profound, and you can get very effective information from this picture. Go to the next, please. Okay, so we go to the result and analysis. As you can see, what we are looking is to find the critical regions within the city, especially industrial cities and big cities. We do not actually look for the precise temperature measurements. Why? Because there are lots of sources of uncertainties in modest pictures, in modest images, due to the atmospheric effects, due to the dust effects, due to the different pollution which exists, clouds, smogs inside the city. So we cannot get rid of these uncertainties fairly, because the correction of these satellite images takes a lot of time. So what we are looking for is the critical region. We have to identify those regions. For this, we accumulate these pictures together. For instance, for 13 continuous day, we just add up these, aggregate these images together and average, and get the average to see which area are critical. Please, next. Oh, yes, go to the next one. Yeah. Next one. Yes, this one. This is the 13 days average JOI LST in August, which is the same time as now. And as you can see, the inset of this area, which is south of Tehran, which is industrial part of Tehran, let's say airport is here, railway is here, and please do not go back. Please go back to, yes. And different part of the city, as you can see, the temperature, the hot point, the red point are in the south and west of Tehran, which is refinery, industrial, airport, those railways, rail station, everything is around here. And you can see the hot point in this area. Go to the next, please. This is the most critical point, which is shown in dark red. This is the most critical point, which takes the highest temperature within the city. And when we go to the field to see which area are this, go to the next, please. We can see the area, which is, please. Yeah, the cemented area and concrete area is in this area. No vegetation, not much water and these things. Go to the next, please. This is the second highest. Go to the next, please. Yeah. Okay. This is the second highest. Again, the second highest class goes to those area. Again, goes to the same area as before. That means the critical point of Tehran is south and west of Tehran, and a little in the east of Tehran. Go to the next, please. The next class is the next class of temperature. Oh, this is a picture from the area which we have gone to see by ourselves. Which area are these? Go to the next, please. The third most critical point goes to the northern part and northeast, and among the around the city center, which are full of roads and highways and buildings, concrete buildings, shows the third most highest temperature region. Go to the next, please. Next, please. Yeah. Okay, go to the next. See, the vegetation is a lot of vegetation in that area. And the next most critical point is here, goes the yellow one, only the roads, highways, and this area at the north of Tehran, which is not that much hot. It is cooler. Go to the next one, please. The least temperature class is here. So the Park Xian, again in the western part of Iran, Chitgar and those area, Chitgar Lake and these area are, although they are in the hot area, but they are themselves a little cooler. Go to the next, please. Okay, concluding remarks. Applying this method to all industrial and big cities may bring this beneficiary for us. Help to locate city heat island. Help to change surface cover and increase albedos. Reduce electricity consumption, fossil fuels consumptions. Go to the next one, please. Reduce greenhouse gas and pollutants. Less water consumption. These are the benefits of running this kind of models on the city, on the big cities. Go ahead, please. Next one. And help to mitigate the effect of drought, of course, which is related to this workshop. Next one, please. Thank you for your patience and forbearance. Thank you a lot. If anybody has any question, just please leave a comment for me. Thank you. We go to the next presenter. Ephraim Ferrari, Mr. Ephraim or Mrs. Ephraim Ferrari, the Afghanistan Drought Early Warning Decision Support Tool. Please go ahead and take your time. Thank you.
Thank you. Thank you, Professor Mubashiri. I'll try to be as fast as a Ferrari, and that's what I usually say. Can you please confirm me that you can hear me?
Yes, I can hear you. Please go ahead.
Fantastic, fantastic. Ladies and gentlemen, very good afternoon. I'm very thankful to the organizer of this workshop for the invitation. I'm Ephraim Ferrari. I'm a consultant working for the World Bank in Afghanistan. And today I will speak about the Afghanistan Drought Early Warning Decision Support Tool that was developed for the Afghanistan government, specifically for the Afghanistan Meteorological Department, by the World Bank with the technical support of the International Water Management Institute, and actually with the very much appreciated technical support from Dr. Giriraj that presented a few sessions before this one. Next slide, please. Very quick summary of the topic of today's presentation from my side. I'll provide the audience a very short and quick overview of the program that is supporting this drought early warning tool. Some very brief background information on Afghanistan and why monitoring and responding to drought is essential for this country. And I will provide some images on how the tool works, and especially also an information of how this tool has been used during these first months of 2021, as unfortunately I would say drought condition emerged over a certain part of Afghanistan. Next slide, please. So the decision support tool that I'll present is part of a larger initiative aimed at supporting the government of Afghanistan shifting from a reactive response to drought to a proactive risk management of drought. What is the difference between these two approaches, I would say? Till today in Afghanistan, the response to drought was usually implemented after the drought impacts were already affecting the livelihood of communities. And once these impacts were affecting the communities, the government would plan and implement relief measure that most often comes as cash distribution or food and water for affected household or feed for livestock and so on. All these actions are defined as post-impact intervention. And very often, worldwide, it's not just the case of Afghanistan, these actions comes late. It's difficult to coordinate them, and ultimately they do not provide a response, a sustainable response to drought effect, and this is the major aspect. So the objective of this initiative, which is called Early Warning, Early Finance and Early Action Project, is really to support the government of Afghanistan in adopting a proactive approach where prevention has a lot of attention, receive a lot of attention. We need to acknowledge the fact that in Afghanistan, drought is a recurrent phenomena, and that most probably will happen in the future as well. So the focus is more on reducing the impacts of drought and develop system procedures and approaches that can help us doing so. It's of course not a simple task. It requires a lot of time, a lot of efforts, and a lot of coordination between agencies. And this is, I feel, a really important aspect. It's not just a technical thing. It requires really a lot of support from all the stakeholders that are involved in this process. There are, I would say, a series of bullets I've listed here in the slide. I would say at least 4 of them are very essential. Of course, one is the drought monitoring and early warning system. that needs to be able to deliver timely and precise information on where drought is happening. And this will be the focus of this presentation, of course, because in a country like Afghanistan, Earth observation tools play a major role, and I'll come back on this aspect. We need also to ensure that there is an enabled political and institutional framework. Policy must be there. Institutions with clear roles and mandates must be empowered so that everybody knows what to do and when in the case of a drought happening. Two other aspects very important are preparedness plan, which needs to build awareness and understanding of the drought hazard among different stakeholders, providing them information on the underlying causes of vulnerability, and making sure that the risk management is streamlined throughout programs from the government at different levels, not only at national level, also down to provincial and of course district level too. And in this regard, testing and conducting exercises on preparedness is really essential. And finally, of course, the emergency response programs, which goes back to the reactive approach we were presenting before, but then needs to be able to provide assistance to these households which are affected by drought, so that they can at least cover their basic needs and continue their livelihood in the place where they are living. We can say that this program, this early warning, early finance and early action program, aims to build this proactive approach by merging early warning with pre-agreed early financing resources and early action, so that basically in case of a drought is identified, financial resources are available to assist the households that are affected by drought, and simultaneously in years which are not drought years, to be able to build the resilience of these households. For example, if we are talking of rain-fed areas, it could be by enhancing water retention capacities, maybe building water channels for irrigation and so on. Next slide, please. So going now, focusing a bit on Afghanistan. Drought in Afghanistan is our current phenomenon. We don't have a lot of data. As you all know, Afghanistan is a country that went through a very long civil war. Unfortunately, also the information coming these days are at all not very positive. And the situation, but if we look at, again, at drought, what we know that at least in the past 2 decades, there has been on average 1 major drought event every decade, and 2 or 3 less widespread events, but they can have been localized, very intense as well, over a decade. So it's a recurrent phenomenon. It happens very often. To give a reference to the people attending this conference, the 2018 drought, which was probably the most severe of the past decade, affected 1/3 of the country and displaced several 100,000 people from the rural areas to the urban areas. And this is, of course, even more important because if we look at this map on the right of the slide, we see that the frequency of drought is higher in the northern part of the country. This northern part of the country is also the portion of country which is mostly where rain-fed agriculture is most common. And of course, we all know that rain-fed agriculture tends to be more vulnerable to drought event as compared to irrigated agriculture. Next slide, please. So, as I was mentioning before, the project is quite comprehensive in terms of activities. This presentation, given we're talking about space technology, will focus on the early warning part, and in particular on the approach developed to on the approach used to develop the early warning tool. This is just one part of let's say the set of activities that we are planning to implement to strengthen the early warning capacities of the government. Of course, one thing is to access precise information. And this is really key in a country as Afghanistan, as I was mentioning, after nearly 40 years of civil war. Of course, the hydromet infrastructure in the country is very scarce. I was looking before at the slide from previous colleagues on Iran and the number of hydromet stations they have used to conduct their studies. In Afghanistan, we do not have, unfortunately, so many weather observatories. There are also gaps in the years where these observatories, the few ones that have been active for a relatively long amount of time, we have gaps in the coverage, so it's really difficult to rely on ground measurement. And in this, let's say, under this situation, of course, satellite remote sensing provide very valuable information, and we will deep dive on this. But this is just one portion of the early warning system. Another very important aspect is to enhance the capacities of particularly government stakeholders, but not only, in conducting drought analytics, and thus share information to decision makers. What we need to do is to catalyze information derived from satellite data and other publicly available sources into easy to understand information for non-technical user. This is really important, and we have started doing this by, for example, producing together with the government counterparts weekly and bi-weekly drought bulletins. And again, I will quickly touch base on this later on. Finally, it's also important to consider institutional support and the coordination, particularly during the emergency, but even before. And this is a key aspect for the disaster risk management agencies. We conducted some preliminary activities, but in the future we plan really to work hard to link the early warning tool with the public alerting and responses, providing information, for example, to farmers on what they shall do in order to reduce the impacts on drought. Let's now focus on the AFDUs, so I kindly ask to move to the next slide. The Afghanistan Drought Early Warning Tool, which I summarize as AFDUs, is an online platform which developed with the objective to provide to the agency mandated to monitor drought condition, and as we are talking of Meteorological Agency, Water Resource Agency, and Ministry of Agriculture, easy to access already processed satellite data to assess the status of drought condition in the country. The tool, as I was mentioned before, has been developed by the International Water Management Institute, is based on Google Earth Engine cloud platform, and thus allows a very quick sharing of information, and what is possibly most important, always updated, already developed and already processed satellite indices. It also includes forecast from the short, medium, and seasonal from the Indian Meteorological Department. And it has all this long list of satellite indices, which we'll see shortly. The tool basically provides all the information to support decision-making by the different agencies. And if we go to the next slide, we'll try to see how does it work. So the AFDUs, as we can see in these two charts, are basically enables the agency to easily access a lot of remote sensing data. Is also capable of providing to these agencies through very simple mechanism the capacity to add context to these data to derive information. And we can derive, by applying meaning to this information, we can derive knowledge. And this knowledge is what is needed to take decision, to allow the authorities to take prompt decision on the status of drought. We have been able to do this thanks to the IMI support by adding layers to the pure, let's say, satellite-based information on NDVI or other indices. We added layers such as type of agriculture, whether it is rain-fed or irrigated, the land cover, information on people livelihood, people density, and other socioeconomic factors. And this basically merged all together really allows the authorities to take prompt decision. I will now focus a bit on the type of information and especially the satellite information that we have been using and how this analysis can be done in a very simple way to inform decision maker once again. So let's go to the next slide, please. Here we have the classic list of indices, and several of those have already been presented. Of course, I won't get into the details, but as you can see, there are several indices pertaining to meteorological drought monitoring, agricultural drought monitoring, and also hydrological drought monitoring. Of course, all of these have importance for different agencies, but overall for the entire country as well. Because of course, for example, in a country like Afghanistan, we know that that the wet season is concentrated into the winter months, probably similar to Iran, I guess, and thus snow accumulation, for example, is really key to understand the availability of water for irrigated agriculture. While for rainfed agriculture, the timing of the precipitation is really important. Precipitation should fall during the early winter, but also the early spring months. So during the time where the crops are growing before the winter vernalization, and also when the crops are re-emerging after winter. In addition to this, we have also the long-range forecast from IMD, which provide perspectives, of course, of what will happen in the next few weeks. Next slide, please. And here we see a few images of how the tool works. It's very handy, it's very simple to operate, and user can derive really in a matter of minutes what would have been until a few years ago very time consuming and very complicated and requiring quite a lot of capacities from the user. So you can, for example, here we see two images from the NDVI. In the top left side is the NDVI from March 2005 and the NDVI from March 2011 on the top right side. And as you can see, these areas are basically the tool allows to overlap the two maps and utilize a scroll to quickly compare the 2 years. So even for a non-technical user that doesn't know much about NDVI, by having this color, it can really easily understand and identify which are the drought affected areas. In the lower side, you see the entire image from 2011, which was a relatively drought affected years. Next slide, please. Another feature of the tool is the ability to download data for different geographical settings, from country-wise data to provincial-wise data or district-wise data, or even for user-defined area. You can download the statistics of whatever indices you want for a time period of up to 20 years, depending a bit on the different satellite data set utilized. And this is, again, very, very useful for more technical user to conduct further statistic and analytics on the drought status over a particular part of the country. Next slide, please. Yeah, this one. Oh, I think is number 3 tool feature. This one, yeah, thank you so much. So here we can see really how to download the data. You just click one button and you derive and you download the data. You can even download the graph or the image in JPG format for easy use into a document, or in CSV or Excel format if you want to conduct further data analytics. Next slide, please. Of course, another important aspect was the definition of key indicators, meaning indicators that can be used for really taking an action. The most important in the indices, we can say, thanks to IMI support, lots of statistical analysis were conducted. I'm not going to enter into the details of this, but we have listed 4 indices with different time period where under which the agency should really push and put efforts in keep monitoring those, because these are really helpful to identify the drought condition in the country. Next slide, please. And this is my last slide, so should be almost in time. This is just a summary of what happened during this year. As I mentioned before, unfortunately, this year was a drought year in Afghanistan, and despite this tool being very developed, let's say, throughout 2020, so being very, very new, it went through what I could say is a sort of baptism by fire. With the Afghanistan Meteorological Department, we initiated the production of bi-weekly drought bulletins and weather forecast, and these were found very useful by the government agency to prepare the drought response strategy well in time. And in June 2021, the president of Afghanistan declared drought condition in the country, utilizing the information provided by the Afghanistan Drought Early Warning Decision Support Tool, and the response strategy is currently being finalized. I'm annexing here one map in the lower right corner, which is the output, I could say, of the use of the FDUs and other information coming from both the Ministry of Agriculture, the National Security and Information Agency of Afghanistan, and the UN. And this is the image of the overall situation. As you can see, over 40% of Afghanistan districts are facing drought condition. And of course, this requires prompt action to be undertaken. So that's all from my side. I think I have one last slide of thanks, Tashakur, to everybody. And if you have any question, please do let me know. Thank you.
Thank you, Mr. Ferrari. Thank you, Dr. Ferrari, for your presentation, your nice presentation. Today we had many presentations and everybody have presented very nice work and nice covered nice problems, except me. And we are almost finished on time, but we are half an hour behind the schedule because 15 minutes we left for discussion, and right now we are behind those time. If Dr. Rawan approves, I can give this time to everybody who has any question to raise this question, and presenters response them. Dr. Rawan?
I think you can take few minutes, definitely, if there is any question. Otherwise, you may conduct some discussion. 15 minutes, 10 minutes. I hope people won't. Okay. I'll accept some delay. Yeah.
Do we need any time? Is there any question?
Question I don't see really on the chart. No.
Mr. Ferrari, they ask for your email. Please leave your email if you wish.
Yes, of course. I will write it here in the box, and then I'll edit the presentation so that everybody can have it on the presentation too.
Okay. Professor Hamid Mubashiri, of course, he's my cousin. He asked a question and he raised his hand. Please give him microphone.
I think finding him. Okay.
Okay.
Yeah.
Thank you very much. Do you hear me? Yeah. Thank you. I really appreciate your efforts and very nice presentation of the data that nowadays, because of the global warming, all the nations are dealing with, and the problem of drought and water is so important. I am a biophysicist, and I wonder if you could tell me how you can join or complement your information with biophysical data, as, for example, the migration of different pests or the vegetation. That, of course, part of it you mentioned, but the other matter is the electromagnetic field. And do you think that the source of the heat that you are recognizing and detecting by satellite doesn't have anything to the sources of the electromagnetic field that is irradiated by satellite from the sky, or the one whose source is which source is on the ground? Thank you very much indeed.
Thank you, Professor Mubashiri. Of course, we cannot, in remote sensing, we cannot go straight forward to find those things you are concerned about. That means we cannot detect, let's say, the locusts or pests or any pests, but the effect they are leaving on the area or the environment they need to spread out within the country, that environmental factors can be detected through the satellite images. So indirectly, we can cooperate with your department and your area of specialties, but not straightforward. Those electromagnetics that you were talking about, we just name all the radiation. They are, they are somehow electromagnetic radiation, sources of radiation, black body radiation, sun reflected, sun irradiance, sun existence, everything is electromagnetic radiation. But as far as I know, you're concerned about those, low frequencies radiation that comes from, let's say, 5G, comes from 4G, comes from BTS antenna or something like this. Oh, I doubted that remote sensing has involved itself in this area. No, I can't. I haven't heard anything around this, about this. Any other question, please? Okay, I will leave it to you, Dr. Rawan, to manage the rest of the session, please.
Well, thank you, Professor, for wonderfully chairing this, and not so much delay, still it's quite good. So wonderful job, and thank you all presenters. And I would like to leave it to our co-organizer Fateme, if she has something to say, announce and close this particular today's session. So
okay, please go ahead.
Okay, thank you very much. Now, I would like to take this opportunity to cordially appreciate the speakers as well as the moderators for presenting and moderating today's sessions. And I hope the presentations have been useful and beneficial and will bring up solution for connecting the crisis management researchers and whom have concerns in this regard. Unfortunately, today we've got a number of disconnection and we had a really hard time getting connected by our side, that I hope some measurements will be taken not to experience any more problems in this regard. I should mention that the next session will start tomorrow morning at 11 o'clock sharp based on the local time in Tehran. Please join a few minutes before the session, and for the respected speakers, please send their slides to Ms. Emma, Secretary of United Nations. I thank you, everyone.